Hello info person, this is Anton, and today we're going to be discussing just a little bit of physics, and specifically something in regards to the physical constants of the universe, which are all essentially these very specific numbers that more or less describe how the universe behaves. And by itself, this list is not particularly long, but what's really impressive here is that a lot of these constants are known with absolutely extreme precision. And that's of course because of a lot of different experiments in the last few decades that were able to directly calculate everything from the more obvious constants, like for example the speed of light, to constants which are extremely difficult to measure, like the gravitational constant, which is actually what we're going to be discussing today. And well, in this case, this is a fundamental number that directly dictates the very structure of the universe. Yet despite of this remains a kind of a frustrating mystery in the modern physics, despite decades and decades of different experiments that try to calculate it. And while in modern physics, it's also sometimes referred to as the big G. And that's because the little g usually just refers to the Earth's gravity. But in this most recent paper that as always you can find in the description, Stefan Schleminger and his team at NIST, or the National Institute of Standards and Technology, has officially released the most recent results of this decade-long attempt to measure this constant with absolutely extreme precision. But unfortunately, instead of solving this mystery once and for all, here the results once again add a new layer of complexity to this problem, despite actually being the most accurate results to date. And so let's talk about this study and the results in a little bit more detail. But first, so what is this big G? And of course, why does it matter so much? For example, even though we don't actually feel it, but you and I right now have a gravitational interaction. It's a very, very small interaction, but it's nevertheless there. And so whether it's two stars in a distant galaxy, or two people watching this video right now, basically you and someone else out there, big G is a kind of a proportionality constant that basically makes Newton's law of gravity work in a nutshell. This is the universal gravitational work. But once again, big G and little g are not the same. Little g is the local acceleration due to gravity, and it's 9.8 meters per second square, which is of course the value for Earth. But if you go to the moon, little g changes because the moon is also less massive. And so in this case, little g is always different. In contrast, the big G is always constant. And as far as we know, and as far as we've measured, it seems to be same everywhere and remain constant for at least the last 9 billion years. At least that's based on the observations from various telescopes and the measurements from various galaxies. But despite these somewhat accurate observations, to date, this particular constant is still the most elusive, or at least the least precisely known of all of the fundamental forces and all of the fundamental constants. For example, we know the speed of light extremely well, and we can even calculate the extremely small Planck constant and the elementary charge of electrons with very, very precise values. As a matter of fact, for these three constants, the relative uncertainty right now is 0. That's essentially how accurate these values are. But in contrast, big G only has a relative uncertainty of about 22 parts per million. And though this might sound kind of small, in the world of modern precision, that's actually super inaccurate. That's basically about 0.002%. And while the reason it's so imprecise and why it's so difficult to measure this constant is actually because gravity is just so weak in comparison to everything else. As a simple analogy, a tiny magnet the size of a pinhead can usually easily lift a paperclip, which of course overcomes the entire gravitational pull from the whole planet Earth. And so yeah, let that sink in for a second. A tiny magnet produces electromagnetic force that's stronger than gravity coming from the entire planet Earth. But in the lab conditions, things become even more difficult. Here, scientists usually have to measure the attraction between very, very small masses that are hundreds of billions of trillions of times smaller than the planet. And at this scale, the forces are so faint that even the slightest environmental change can usually ruin the measurements. But to measure this, usually scientists use something like this. There are essentially two separate massive bodies suspended on some kind of a torsion wire that are then positioned in such a way that they're slightly farther from each other at a certain known distance, and the scientists just have to wait for them to eventually touch each other, in the process discovering the gravitational attraction. This is actually a pretty cool experiment to try to do at home one day, but it can actually take a very long time, sometimes weeks. And so to try to solve some of these discrepancies and to try to calculate a more accurate value, the team at NIST that you see right here spent the last 10 years replicating a famous 2007 experiment originally conducted by the International Bureau of Weights and Measurements. This is a very similar agency, but in France instead of US. And they actually used the same instrument referred to as the torsion balance. Although in this case, instead of just using a bunch of balls hanging on a string, scientists used a much more precise apparatus with aluminum cups and brass balls that would attract each other using gravitational forces. And so here, by suspending a small disk with larger masses placed on it, this would actually cause the ribbon to twist slightly, producing the effects of torsion. And so by measuring this tiny twist, or by using electrical voltages to prevent the twist from happening, essentially counteracting the twist, researchers can then try to estimate the exact value for this big G. And so in essence, it's kind of similar to this experiment, but here, the electromagnetic forces, whose constants are very well known to us, are then used to try to counteract the gravity in order to calculate everything. Although in this case, to avoid any kind of a subconscious bias, researchers also used what's known as a blind analysis, where they essentially had a secret random number from the data subtracted from the results. And so in this case, researchers did not actually know the true value for the constant until they opened a sealed envelope during a public presentation in 2024. And when they opened the envelope, the results were kind of surprising. They discovered the value to be 6.67387 times 10 to the minus 11 cubic meter per kilogram per second square. Okay, I know this is quite a mouthful, but in essence, they discovered a value that was 0.0235% lower than the original French result from 2007. And 0.02% is once again quite significant. And significant because in high-precision physics, we do expect results from the same equipment to usually match. As a matter of fact, if you look at some of the previous measurements, you'll notice that quite a few of them seem to be in a completely different place and not match at all. And in this case, it also includes the results from the French experiments in 2007 and earlier. And so here this is kind of unexpected, but also confirms that there are still some unrecognized instrumental effects or some kind of a hidden systematic error that we still don't understand when it comes to measuring gravity. And so here scientists now refer to this as dark uncertainty. Okay, maybe not the best name again, since we have dark matter and dark energy and stuff, but really it's just because nobody knows what's going on. And so here it's a way of acknowledging that there seem to be unexplained differences between best experiments and most accurate calculations and the actual results. And so at the moment, nobody actually knows what's going on. And so I guess the next question is, so what's next and what challenges remain? Well, in this case, researchers do highlight at least several subtle challenges. First one is the thermal torque. In this case, the team discovered that tiny temperature differences, as small as 5 millionths of a degree, can actually cause air inside the vacuum chamber to move just a little bit. And so sometimes it creates a kind of a thermal torque that seems to mimic gravity. In other words, even though this is done in vacuum, since it's not perfect vacuum, there are still some uncertainties. Then we have geometric imperfections. The metal masses that are used in these experiments are not perfect spheres. I mean, they are perfect spheres to our eyes, but on atomic scales, they do contain occasional irregularities, and some of them were discovered to have trilobate shape errors of just a few micrometers. And so even though this just involves like a few hundred atoms or so, it seems to produce enough bias in the results. And lastly, there is the instrumentational limit. Certain sensors used to measure the twisting angle, the instruments referred to as autocollimators, usually have to be calibrated at specialized labs in Germany. This is in order to account for various errors a few billionths of a degree in size. And so in this case, there might have been a calibration error with the results produced by these instruments measuring slightly different angles of separation. In other words, there are quite a few potential errors, and right now resolving this would be kind of challenging. But these results still matter quite a lot, at least for some of the future experiments. And so even though we did not get some kind of a single number from this new measurement, this is still a massive step forward in trying to basically bring order to the universe. Or at least in trying to calculate how the universe behaves at cosmological scales. And so in this case, by identifying some of these new sources of error, like for example the thermal torque and the differences in mass shapes, the team can now provide a new roadmap for the next generation of scientists. In other words, by modifying this type of an experiment, or possibly creating a completely new type of an experiment and using a different setup, we might get a much more precise data next time. And so in this case, this is really not about this final number, as much as trying to expose some of these unknowns, which could also cause some of the additional errors in other experiments using something very similar. And so every time scientists get an experiment that doesn't go as planned or produces incorrect results, we actually end up getting just a little bit closer to that final truth. But at least for now, as of early 2026, the gravitational constant, also known as the Big G, remains a mystery. We still have no idea what the exact value is, which means that we must press on. And that's because it measures one of 4 fundamental forces that we still don't really understand very well. And since gravity is all around us and basically dictates the entire universe, it's one of those forces that we need to understand in order to try to answer a lot of different questions in the universe. Which means that we'll come back and discuss this more in some of the future videos. Until then, thank you for watching, subscribe, come back tomorrow to learn something else, support the channel on Patreon where you can find additional videos without any ads and can DM me directly, or by joining a channel membership that grants you early access. You can also support this channel by buying the Wonderful Person t-shirt in the description below. Stay wonderful, I'll see you tomorrow, and as always, bye bye.